Okay, so do you see my screen? Everything is all right?
Yes.
Okay, so welcome everyone. So this is the last lecture for the course Software Architecture. And though we have many other things, we have um, two more assignments to go through and a project. And finally, there will be a final exam. So for these assignments and for the project, we will see each other within those meetings. So microservices architectural style is discussed in this course in your course book on in chapter 17. So let's get started. So microservices architecture style is becoming really popular over the years. And we can say that it is the newest and youngest among all the architectural styles that we have studied so far in this course. And it is gaining a lot of momentum, and it is actually based on domain driven design. It is an extreme form of domain driven design. So the term microservices actually got famous from a blog entry written by Martin Fowler and James Lewis in March 2014. Uh, Before that, we usually called this kind of architecture domain-driven design, but now it is called microservices. So it is heavily inspired by domain-driven design, and especially especially the focus is on something called bounded context. So this bounded context is a concept for coming from domain-driven design, and it advocates that um, we should, the services that we build or the components that we build, they should be highly decoupled from each other. And the real thing here, that allows us to see how microservices actually work is this line. It promotes duplication over reuse. So it's really important. For instance, if we look at service-oriented architectural style that we studied before, it focused on reuse as much as we can, depending, because of the time that architectural style was developed. But this one, microservices, the latest, architectural style that we have today, it advocates duplication over reuse. It says that whatever need to be designed or needed for one bounded context should be implemented within one microservice. Does not matter how much we need to how much we need to duplicate components or things. So that is not an issue for us. So on one side, we had service-oriented architecture, which was highly influenced by the principle that we should reuse software as much as we can. And microservices is on the other spectrum, saying that we must duplicate as much as we can. So the concept is that we must promote duplication to achieve highly decoupled services that do not depend on each other. So this is how the topology looks like. And I will just try to hide this one. Yeah, okay. So as you can see in this topology, we have a service over here having its own database, then another service having its own database, and so on and so forth. A number of services, and of course, sometimes services need to synchronize their data. Services needs to communicate with each other. So showing these arrows for that kind of uh, communication. So for instance, here we are using queues so that data could be transmitted from this database to this one. So then we can have something like an API layer, how the outer world, how we will use these services. So these services can be provided through APIs. API layer can be on top here. So a client request comes in, and let's say it is about customers. Let's say it's about customers demographics. So probably maybe it will go to this service that deals with customer demographics. Let's say another request comes from client, and it is about updating our data warehouse. And let's assume that this service deals with that kind of all the things related to data warehousing. So we have this one over here. And sometimes they need to communicate. So this arrow represents that. So the idea is that each service that we have here is a single purpose functions. So each service fulfills one function, one and only function. Okay. So it doesn't do more than one, only one function, and that function will be a service of its own. So single purpose functions deployed as separate units with each unit owning their own data. So that could be a database or something else. So as I have just talked that it's a single purpose, separately deployable. Yeah, this is also very important. So all these services, these are deployed separately in containers or over the internet or over the network. So it can be the same machine, but in different containers, or it can be on multiple machines over communicating with each other through internet or through the network. So it's a single purpose, separately deployable unit of software that does one thing well. So it provides one functionality well. So due to its single purpose nature, the service size in microservices can be much smaller because it only performs one function, as opposed to the services or the software we had or components we had in service-oriented architecture. In service-oriented architecture, components can be really big, large, but here, since each service tries to provide one functionality, that is why it is called microservices. And the size is smaller. So microservices does not necessarily means that it is smaller in size. Microservices really mean that it provides only one functionality, one service. So in ideal world, what we try to do in microservices architecture is we expect that uh, each service has everything it needs on its own. Within that service, it has everything that this functionality we need to perform a functionality. It's an ideal scenario. I mean, many times we will be violating that, but the ideal scenario we want to have is that whatever components, things, data we need related to this functionality that this service provides must come from the same service. It should not have to go out from it. But of course, it's an ideal scenario, which is really hard to have in real world applications. But this is what ideal scenario looks like, at least in microservices. So second thing is that microservices are formed, it is a distributed architecture. So each service runs typically in its own process, in its own virtual machine, or in its own container. It can be a separate virtual machine, or it can be in a separate container. So containerization,
I have a
uh,
question.
yes,
Sorry.
sure, yes.
Can you explain containers, how they work
Yes.
more?
Yeah, so if you like, we did not go through containers in this course much, but if we look at, I can give you some names like Docker. Okay, so if you go and search for Docker, there are some technologies, open source as well as commercial, that allows you to have different kind of environments on the same operating system. So for instance, if I install Docker on my machine, and within that I can create small containers. So let's try to understand what virtual machine is first. So I am running right now Windows, and within that Windows operating system, what I can do is, so this is my operating system. I can install uh, through a virtual machine, let's say running Linux, let's say Ubuntu. The problem is when I'm running, so my Windows is running and Ubuntu is running. But the problem with the virtual machine is that I have to allocate RAM, hard disk, everything. So it's a virtual machine. It looks like exact, machine or laptop that I have physically. So I can have one virtual machine running Ubuntu. I can have another virtual machine running maybe Windows Server, and so on and so forth. Given that how much memory and powerful machine I have, I can create many virtual machines. So the problem with this kind of setup is that virtual machines take much more resources. Okay, so one container or one service can run here, one service or container can run here, another one can run here, and other one can run here. Why I need to separate? Because maybe this one is using maybe Python 2.7, this one is using Python 2.6, sorry 3.8, and this one may be running another environment, and this one running another environment. Separating them into their own virtual machines allow us to uh, create the environment in such a way that there are no conflicts. So imagine like maybe I have one more virtual machine running Android Studio in a certain versioning, and then if I try to install another Android version, then there can be conflicts. So virtual machines allows us to have different kind of setups on one machine. But problem, as I said, they are very heavy. So you can't, your machine will start to struggle when you add too many virtual machines. What is the easier way to come out of it? Well, an easier way to come out of it is containers. So containers, as the name suggests, if you go to the Docker page on Google, if you search it, it shows, a ship. And then on top of it, there are so many containers, just like logistic containers, that we send every day from one place to another. There are so many containers. A container is just like the goods container. So each container has its own closed environment. So this container can run one service, another container can run another service with all the compilers and environment that is needed for that uh, service to run. So, and these are really lightweight. Here is the main thing that is important to remember is that these are really light computationally, light things to have. So virtual machines were heavy. Doing the same thing, you can have now containers, Docker containers, and these are really lightweight, allowing you to have multiple services or environments, development environments or machines running on the same system. So this is what containers are. Okay. So microservices form a distributed architecture. So where they run, these services run in its own processes. You see, in its own processes mean it can be run through within its own virtual machine or within its own container. When you have a container, it has everything separate. It's like a house, and then within that house, you have a small room. Whatever happens in that room, the remaining house is not affected by it. So that is the concept. So why do we do that? Because separating each service into its own process solves all the problems brought by sharing. So service-oriented architecture was all about sharing, and that was one extreme. Now we are in the other extreme. Microservices do not share anything. That is what microservices are. So do not share anything. So how we do not share anything? By putting those services into isolated containers that, you know, are completely independent, isolated from each other. So that is the idea. So, coming back to our point, so separating each service into its own process solves all the problems brought by sharing. So all the problems we discuss with service-oriented architecture, they go away in microservices architectural style. So with cloud resources and container technology, teams can reap the benefits of extreme decoupling. Everything is decoupled. You don't depend on each other. No service depend on other within how that thing is solved, both at domain and operational level. So what is domain? Domain is like in terms of functionality, um, or the business process you want to achieve in one service. It is completely independent from uh, business process point of view, but also from operational point of view. So operational point of view is something like that. Let's say we have a service running on this container, and over here, we have some kind of operational software looking at how much stressed this service is because of the requests. People are, how much pressure or how much traffic is going here. So it is monitored by this piece of software looking at how much stress is in right now that this service is performing in. So this can, on operational level, looking at how much pressure it is in, let's say uh, 80% or let's say 75%. And programmatically, we can start a new container, same duplicate, increasing its capacity. Now, half of the request can go here and half of the request can go there. And now we realize that after some time there is, really small low traffic. So we can shut down one of the service and let one service up and running. So these kind of concerns are operational level concerns. So when you have microservices and one service does one thing, uh, 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 as much, one thing only, then you can start more, add more machines to it when there was a lot of load on it, and shut down when there is not much load on that service. So that is what operational level means here. So separating services into, their own containers allows us to do that. Okay, so microservices distributed nature impact performance because everything is happening on a distributed level. So network calls are slower. Security verification needs to be done on each endpoint. So whatever endpoint your service exposed to needs to be checked. Who is coming in? Do they have sufficient rights to invoke that service? So this needs to be checked all the time. So it impacts performance. So the use of transactions. So this is also a kind of principle. Like we want to avoid this service depending on this service too much. That is, in principle, microservices should not depend on each other. So this is what we discuss here. The use of transactions across service boundaries must be avoided, though in practical, it is highly difficult to achieve that. Because if you really do not want this service to depend anything outside of it, then you will end up with a big, large monolith here, doing everything by itself. So then it won't be any microservices to begin with. Because in real life, things depend on each other. So we really cannot fully have this, there will always be some dependencies. So we need to be ready. But in principle, it must be avoided, the dependencies. So the concept here is, again, we are saying that microservices is all about share nothing. So it is sometimes also called share nothing architecture. So the bounded context says that they, a service will not share anything. So what does it mean? It means that the granularity of a service, of each service is the key to success in this architecture. So when you are building a microservice architecture, and if you as an architect, you are able to separate services in such a way that they do not much depend on each other, then you really become successful with the task. So the driving philosophy of microservices is that each service models a domain or workflow. So a domain should be covered in each service, or a complete workflow is covered. Whatever business process you can think of, the whole process should be done by one service so that it does not require to depend on other microservices. So thus each service includes everything necessary to operate within the application, including classes, some subcomponents, and database schemas also. So everything should be within that service. So again, as we said, microservices prefer duplication instead of coupling. It's all right to create a similar subcomponent in each one of those microservices. It's all right. Duplication is no problem uh, in microservices. What is important is that we do not share things, because when we share, then we have coupling, and coupling is the problem. Here we want to isolate services as much as we can. So granularity of services means uh, one, just like a grain of rice, one service is really solid. Everything happens within itself, but it does not depend on other services. Okay, so uh, again, so in that way, we can say that microservices take the concept of domain partitioned architecture or domain driven architecture to an extreme. So it's really going to another extreme. So each service is meant to represent domain or subdomains, and microservices are actually the physical manifestation, because what you will do, you will have a microservice and you will really install that service into some container. So it's really a physical manifestation of the logical concepts in domain-driven design. In domain-driven design, you end up thinking about a workflow or a domain, let's say employees. And then you have everything about employees in one microservice, and then you install that microservice into some container. Then you really, what we can say in this example, that microservices becomes really a physical manifestation of the logical concepts that we usually have in domain-driven design. Everything about employees goes to one service. So granularity, again, we are still, we are just trying to understand with more and more details. So the problem is that uh, how can we achieve granularity? So finding correct granularity for a service is not easy, as I said. In real life, things, we depend on many things. So nothing happens in isolation. But microservices says that try to isolate as much as possible. So we need to, it's not easy task to do. So we need to find a sweet spot. So was services too small requires communication between the services to do the useful work. So your services is really too small, doing just one thing and one and only, then you are dependent on other services. But if you try to put everything in one service, then it will become so large that it will look like as a monolith. And then you need to be in the middle of these two extremes. So that is very hard to do in actually real life, and very much painful when you are designing microservices. So as you know, as I said before, microservices does not need to be micro. Micro only means single purpose functions here. Micro doesn't mean that it is a very small service. No, what it means is that it does one functionality right, though it could be a lot of components within that service. It is still a microservice because it fulfills single purpose function. It provides a single purpose functionality. So what can be the guidelines if you want to find appropriate boundaries for your services? So you need to look at the purpose of each microservice. So when you are designing your microservices, you look at purposes. So a microservice should be extremely functionally cohesive. So it should serve one purpose. And when you look at from this perspective, you will be able to design good microservices. So one significant behavior on behalf of overall application. And then comes transactions. You look at your business workflows or transactions. So bounded context are business workflows. So whatever is needed to complete a business workflow, let's say opening a bank account or let's say checking out and within an e-commerce service, it should happen within one microservice. So you can look at purpose, you can look at transactions or business workflows just to define the boundaries or granularity of your microservice. And finally, choreography. So how, uh, so for instance, if you end up having two or three microservices that need to kind of talk to each other, you need to define how they will talk to each other, how functionally cohesive they can be bundled together. So a set of services that offer excellent domain isolation yet require extensive communication to function could be bundled into a larger service to avoid communication overhead. So imagine a situation you have a customer related microservice, and then you have, let's say, a transaction related microservice in within an e-commerce application. And customer and because customer buy things within an application, so maybe customer service needs to communicate with um, the e-commerce service, and you have to think about bundling them together in such a way that they are close to in one geo location, maybe within one local area network, maybe within one local machine. Maybe you try to let them communicate through synchronous messaging instead of asynchronous. So these kind of things can also help you to really bundle those separate services closer to each other so that they look like one function, one um, system from the outside. So three things when you are defining the granularity of your microservices: look at the purpose, look at the transactions or business workflows, and look at how, if these are two or three sub domains or sub functionalities, how they will talk to each other, put them together close enough.
I have a
Yes,
question.
yes,
Should each business workflow only be completed in one
yes.
microservice? Only with
Ideally,
one?
it should be like this, but in practice, it's really hard to do that. Okay.
Yeah.
Yeah. So let's look at, so we talked about right now, microservices require separating domains, defining granularity related to the business workflows and the purpose, right? There is another way of looking at it. You also need to separate your data within these databases. As you can see that it has a service having some modules. And of course, this service depends on database or data. So each service will have its own data also. So it's not one large, big database now. Each service will have its own database separate from other services, as you can see. However, if you really need to synchronize things, you will use queues. You will use some ways to synchronize data or to fetch data. Sometimes, like for instance, when you are fulfilling the request through this service, and this service really need to fetch some data from this service, we will see some of these patterns. It will send a request, get back here, and then sends here. But ideally, let's say this service is about employees. This service is about, let's say, account information. This is about data warehouse. So everything about data warehouse will be in this database. Everything about employees will be in this database. So you will separate these databases also. Data isolation, we can call it. So another requirement for of microservices is that you once you have separated, the domains, you have separated the services, you also separate tables, data, relations, and so on. So you cannot have a unifying database anymore. It will be multiple databases. And here is an example, for instance, here instead of considering them full-fledged databases, think of them some schemas, smaller schemas that you have here. Few tables here, few tables here, few tables here related to these services. So you got two alternatives here. The first one is discussed here. So what you can do is identify one domain as source of truth. Let's say among these three domains, you decided that this one is my main domain where I will keep my data. This one, this one. So then it will become your source of truth. And whenever data is changed here, you update other dependent services that also depend on this data. Okay. So using database replication or caching to distribute information. Once now you have decided that this is your main source of truth, whatever, whenever it is changed, you will update others, whoever is dependent on this data, you will update those databases also using some, caching or data replication techniques. However, in principle, what you will have is within microservices architecture, each service will have its own DB tool. And once you have, once you separate your databases here, now this can be maybe using MySQL server. This can be, MySQL. This can be maybe Oracle. Another one could be just CSV files. So you got this independence also. Each service will have its own way of storing that data the way they like. So each service can choose appropriate DB tool based on their price, type of storage, and host, or any other factors that you may have to think about. Like imagine this one, this kind of here, you have vector data, uh, vector database, like for instance, you have data related to videos, images, a lot of that kind of data, then probably you don't need conventional database here. You would probably go for some kind of, we call it data lakes. Whatever is appropriate for each service, you can now have that kind of database tool or database storing that information. So we learned about two things. A service is serving one functionality or business process or domain. Then database, similar kind of data needed for this business process or entity or domain. is stored here. And then comes API layer over here, this one. So it is, by the way, an optional component. You may or may not want to have this API layer. Here, the idea is that all the requests will come from this API layer. It can be some kind of API implemented in RESTful API, just like you did that in your lab number 2, assignment 2. So it can be that an endpoint through which you can communicate to this service. It's always good to have an additional layer so that your service is not directly exposed. So you expose your service through some API layer where you put, all the security mechanisms, and through this API layer, your functionality is exposed to the outer world uh, with well-defined ways you have already defined. So it's an optional layer, by the way, but typically it's better to have it. So it acts as a gateway between, the request and the service, as we have seen in assignment 2 also. So, and then it is good to have it because it can work as a routing or as a proxy, and it can also, allows you to take care of some operational facilities. Like you can see how much, under pressure this service is. So operational things can also be taken care if you provide this API, these functionalities through this API layer. So, but it should not do anything further than that. It is just an API layer through that you, request services from this microservice. So nothing more than that. So orchestration tool or mediator, no, it will not do those. It's just an API, just like RESTful API, fulfilling the needs of this client. So this through this gateway you can access the service of this, but it's an optional thing. Then operational reuse. So one thing that we can have, okay, let me just hide this part. One thing that we also can have over here is, you see, this is service number 1 that we have here. And this service has many common components like monitoring, some component related to monitoring, logging, everything that happens, all the transactions are logged into some log file so that later on we can go on and check what happened. Especially logging happens when some error happens, when the service is degraded. All these things are being logged into the system. And then circuit breaker. Circuit breaker is a kind of a piece of software that can shut down the service, restart the service. That kind of functionalities can be provided. So this component fulfills the need of operations. You are logging everything, all the transaction happening in a log file. You can start it, shut down it, restart. That kind of things happens due to circuit breaker component. And you can monitor what is happening in some screen, in some console. Um, and all that is happening not only for this service, but also for this service and all the services that you have. So basically you are really, doing the same thing over and over again. So, and this component is also not related to domain. So if you somehow can let them communicate through some service channel, for instance, how and why we need that. Let's say I am depending on some third-party API to provide me this circuit breaker functionality and logging and monitoring. And now there is a newer version. So I updated that version here. Then I need to do the same thing on this service. And I need to do the same thing on third service, and so on and so forth. So what we can do here is we can use something called sidecar component. As you can see that this is a Vespa kind of scooter, and it has this sidecar. This sidecar is just a space, a place where the main rider is sitting on this here, on this scooter, and another one can sit right here. So all the things, the functionality happens in this scooter here. This is just something you carry with you. So you can consider these components very much similar. It has nothing to do with the main service. This service maybe provides you things about employee, this one about accounts, this one about something else, and so on. But these are just side, this is just some operational piece of software you need in those services. So what we can do is we can allow operational reuse of these components, so that when I update this one automatically upgrades. When I upgrade this one automatically upgrades. So that could be done through sidecar pattern. So sidecar pattern, what it says is that we got a service bus or plane, and basically these sidecar pattern, components here and here are connected through this plane. And if I upgrade it here, it will be upgraded here as well. So uh, this allows us operational reuse. So given that microservices prefer duplication to coupling, we have one here and we have one there, but it increases the problem, like you have to upgrade everything one by one. Let's say you got 30 microservices. So it's a lot of work. So how can we get benefit from coupling? We can use something called sidecar, because it is not really about the main functionality of your service. It is only about operations, like monitoring, showing you how your service is doing, logging the mistakes and whatever transaction happens, and shutting it down, starting, restarting, and that kind of things. So sidecar pattern can happen, you can utilize it. Now you will upgrade it here and it will be upgraded in all those services. So this is called, sidecar pattern, and it is usually used in microservices architecture. And sooner or later, you see, you have two services here, one service and second service. This service does one thing, this service does another thing. And in enterprise systems, you have so many functionalities. This service does one, this service does another, this service does another. So there are 30, 40 microservices who are working together to give you whole system. Okay. So when you have that whole system, it is really important for us to view that system somewhere. We want to have a console where I can see how the whole system, how the system as a whole is performing. So if I just take you back over this here, over here, I want to have this kind of control, so that I sit on my computer, or I sit on some one operational room with many, many screens on it, showing me the situation of these services, how they are performing, how much under stress they are, how free they are. So we as when the system is up and running, the banking system or any other major system, financial system, we want to monitor that uh, when it is running. So that kind of monitoring, we need some kind of console that gives us a holistic view of our whole system, because microservices are really micro, one functionality in one service. We want to have a holistic view of our system, how things are happening. So for that, we can use service, something called service mesh. So each service forms a node in the overall mesh, and through the service mesh, you can see it. You can look at some consoles to see how everything is looking for your system. So the service mesh forms a holistic view of the operational aspects of your microservices system, the system that is based on microservices. So let's go through further. What else do we have here? So each service forms a node in the overall mesh. This is one service, this is another one, this is another one. And these lines show that it can be a sidecar pattern also. So some things are being shared, and this could also be some kind of dependency that these microservices have on each other. Because ideally, we cannot have services that do not depend on each other. So sometimes they will depend on each other. So these lines show that kind of dependencies. So architects use service discovery as a way to build elasticity. You see, when you are looking at this console, you can see what kind of services are under pressure, and then you can introduce more compute to those services. Rather than invoking a single service, a request goes through a service discovery tool. So then you will have a kind of service discovery tool, which can monitor the number of, it can monitor how many requests are made, what is the frequency of requests, how much time, how idle your CPU stays, or how busy CPU remains. And based on that, looking at this mesh, what we can do is we can introduce more compute power so that our system remains scalable and elastic. So service discovery is often included in the service mesh, making it part of every microservice. So it will be within each and every microservice through this component we talked about, sidecar component. Through that, scalability is provided. Okay, then let's discuss about the front ends. So for instance, here, uh, you can have one monolithic user interface, or you can have many components separated from each other. Microservices architecture allow you both, but if you have one, then it will be, so if you have a monolithic user interface here, it will be much easier to have, because you have just one simple uh, uh, an effort that you will put in to build that monolithic user interface. It will be a smaller effort, and it will be much simpler. And through this monolithic user interface, you can interact with all these services uh, whenever you need a certain kind of functionality. Or you can have that here, like micro front end. So one component for this service, one UI component for this one UI component for this one. What it does is it can take a lot of effort from you, but at least it gives you agility and maintainability. I can separately improve that UI component without affecting the remaining components. I can simply, upgrade this UI component by not affecting other UI components altogether. So this is both options are available to us, and we can implement our microservices front end any way we like. Of course, with plus and minus, this is much simpler, less initial cost, but this one is it will be more cost here. But and you assemble them separately dynamically, but it will be more cost and more complex. How communication happens within these microservices? Well, generally, you have to decide if the communication between these microservices should happen synchronously or asynchronously. But in microservices, what we say is that it is better to have asynchronous communication, of course, with an overhead. With asynchronous communication, we have overhead. However, what we usually do, doesn't matter if it is synchronous or asynchronous, we try to utilize microservices architecture, typically utilize protocol aware, heterogeneous interoperability. Very difficult, phrase. Let's break it down slowly. Protocol aware. It's a very simple thing. Protocol aware, all it means is that I am the user of a microservice. Okay. So my application, let's say I'm an application depending on a microservice. So I should know what protocol microservice uses. Is it using RESTful API? Is it using messages queues? Is it using service oriented architecture, SOAP, service oriented architecture protocol service, or whatever? So whatever protocol we are depending on, it should be communicated with all other services that look, I am this certain microservice, and this is how you can communicate with me. That is called being protocol aware. Heterogeneous, homogeneous and heterogeneous. Heterogeneous simply means this is the idea, you see, uh, all these services are independent from each other. All they need to do is they need to decide the communication on these gate points, endpoints. So this says, okay, I will talk in REST. Let's say for simplicity, this one also say I will talk in REST. And this also says I will talk in REST. A very common way of communicating these days. All these are now they agreed that communication will happen using REST, protocol aware. Now everyone knows what protocol has been used. It's a RESTful API. Great. And then once you do that, the inner workings of each service becomes heterogeneous. So how I do that, how do I implement that service here is none of concern for this one and this one. I can do this one in Python, and I can do this one in Java, and I can do this one maybe in a COBOL, very old library I'm using. COBOL, some, insurance calculation and stuff like that. It happens in COBOL. You see, that makes it heterogeneous. So these services, once we are protocol aware, once we know that our microservice architecture will communicate how with each other, RESTful API, messages queue, or whatever, then the microservices can become really heterogeneous. This is what it says here. So heterogeneous means you can have polyglot environments, different in kind of environments. In one service, you can run Windows machine. In another one, you can run, Linux. In another one, you can run something else. Uh, Within that, you can have different kind of programming languages, different databases, different platforms. All this is now available to us. We are independent to develop these services separately, independently. Our focus is only on functionality. That's all we care. Focus is on functionality. Choose the best tools for the job, regardless of technology stack. Maybe one in JavaScript, another one in Java, another one in something else. We don't care. And through that, we achieve interoperability. Through protocol aware, heterogeneous nature of this microservices, we receive interoperability. So we can decide all this communication will happen over normal HTTP, or network based communication will happen. So now when we say that, we don't have to worry about how that communication will happen on network level. Every operating system, every tool knows how packets should go, how they should be received. It's well studied problem, and we don't need to worry about that. So services collaborates and exchange data over the network. That is what interoperability means. In, so we depend on the existing infrastructure of networks. Where the way they do communication, we don't care. Let them do the way they want. Limited transaction calls. Prefer asynchronous communication for decoupling and scalability. And then focus on API contracts. Again, this brings us here. So when you are defining how these services will communicate to each other, just focus on what contracts they must follow. For instance, if I have an API to add numbers, so an API through, let's say, calculator, for a calculator. So let's say local host slash, and my calculator is available here, calc, and then I can say add 1 comma 3, and this API call should return me 4. So all we need to do is we need to agree how this call will happen. So this is what we are talking about here. Focus on API contracts, how APIs will interact with each other. You define clear interfaces for your services. You did that in your assignment number 2. And if you do that, then rest is no problem. Okay, now we need to also talk about, because we have, many services, how they work together to achieve the whole functionality together. And we are familiar with only two possibilities. It could be choreography. So where consider each person here knowing what they're supposed to do. That would be choreography. Every component knows, every microservice know what they're supposed to do. Or it could be orchestration. Every component is looking at some main component and follow through the instructions what he or she provides. So two ways we will see both of them, how they also work in microservices. We also have seen them in event driven architecture, if you remember. So you will see some similarities now. So first let's talk about choreography. So we are now here. Every component knows what they're supposed to do, independent from each other, just like choreography in event driven architecture. So in choreography, each service calls other services as needed without a central mediator. First thing, please remember, we want these services to be as independent as possible. But in real life, it cannot happen 100%. So sometimes you will depend on other services. And this is one of those request or example we are looking at. Imagine you got one microservice about customer wish list, one microservice about customer demographics, and the customer wants to get a wish list for customer 123. So this request comes, this customer, he or she wants to fetch his wish list within the system. And let's say the customer's ID is 123. So we really want to get a wish list for this customer whose ID is 123. So request will come from here in through this API layer, goes here, and then customer wish list has everything about this customer's wish list, but it does not have information about, let's say, the name of this customer. Okay, where the name of this customer or address of or phone number or these kind of things live. These are in customer demographics service. So in that scenario, customer wish list service should fetch this information, get name by calling this API, and calling through some API, get the name of customer 123 from this customer demographics microservice. So it calls maybe a RESTful API and sends it, get me name for customer ID 123, and it is returned back mark. So now this customer wish list nicely display all the wish list that was over here, but also saying something like, welcome Mark, here is your customers, here is your wish list, and the wish list is shown. So that could be an example of a choreography. So this customer wish list knows what he or she is supposed to do, and this customer demographic microservice knows what they supposed to do, but sometimes they depend on each other like that. Okay. So in choreography, each service call, each service calls other service as needed without a central mediator. There is no central mediator, as you can see. So it is something like, just like two peers, two microservices working in isolation. And when this uh, customer wish list was working in isolation, it needed some information from this customer demographics. So it asks for it, gets back, and then completes its task. So this is what choreography looks like. So choreography utilizes the same communication style as broker in event-driven architectural style. So there is no central coordinator exist, respecting the bounded context philosophy. So it is still, we are respecting the bounded context since customer wish list is in charge of everything about wish list. But when it requires some further information from other services, it can simply ask. And when it is returned, it will fulfill the request um, for the purpose this customer wish list to business process was created, microservice was created. So from this perspective here, your goal as an architect in microservices should be favor decoupling. Okay. uh, and when we do that, like as we can see here, it resembles broker event-driven architectural style. So there are some similarity. Now let us look at orchestration. In orchestration, if you remember, there is this mediator in between. This mediator will allow that who will do what between two or more than two microservices. So when we see orchestration implemented in microservices, it can look like this. You can have a mediator service on top of two microservices. So this is a microservice, this is a microservice, this is a microservice, but this is a mediator microservice. So it knows that in order to get all data, get all data from customer 1, 2, 3, it needs to fetch demographic information from this and customer's wish list or whatever transactions happens before cards and all that should be coming from here. And yeah, there could be another one also, like shopping cart related. There can be one more service and whatever that is. So this service is responsible for bringing whatever is needed to fulfill the request here, fulfill this business process. And now what you can do is uh, in the microservices architecture, you can try to put them together close enough, maybe in different containers, but in a physically in a same local area network so that the communication is really fast between them. So microservices architecture doesn't include a global mediator like service-oriented architectural style. In service-oriented architectural style, we had a global mediator uh, uh, um, connecting business services to uh, basic services. But here, it's just a small service to complete one business process about customers. So if an architect needs to coordinate across several services, they can create their own localized mediator. So that would be orchestration. And then developers create a service. So we just discussed that. So developers create a service whose sole responsibility is to coordinate the calls of getting all the information, let's say for customers. So this service mediator that you have, its purpose is to fetch information from different microservices uh, about customer and displaying it here. Let me see the time. Okay, so we can take a break here now, um, and then we will return. Let's say when we will return. So 17
20.
20. Yeah, thank you. Okay, so let's come back at 1720.
Sounds great.
Okay, so let's get started again. So we were discussing orchestration, and now let's follow through one example for a choreography, and then one more example for orchestration. So let's start with an example for choreography. So let me just check quickly. Am I recording the session? Yeah. Okay. My screen is shared. Yes. Okay. So let's look at this example, like place an order to purchase a book. So as you can see that now it's a complex business process. Let's assume we have some microservices like order placement, payment, and inventory. So in that case, in choreography, what will happen? One microservice will assume the role of a workflow owner. So let's say it is order placement, and how it will happen? It will happen, of course, through code. So within that microservice, we will program it in such a way that uh, whenever about placing an order to purchase a book, this process happens. This order placement will become an honor workflow, and this microservice will communicate to all other microservices and fetch data that is needed for this uh, process to be completed. So for instance, let's say order placement is happening here, and within that transaction, we need to pay for an order. So pay for order happens through this microservice, and then a response comes back. And then let's say since order was successful, we need to update the inventory. So order placement will send a request to update inventory, and then a response comes back. That means inventory is also being updated. And then order placement is successful, and it can send back appropriate screen or message to the customer. So in this, as we can see that this order placement service must coordinate. It is coordinating with other services. So it is actually acting as a basic mediator between different microservices. So this example that we just looked up right now, looked upon, it is called front controller pattern. So this is the front controller pattern. It usually works for, you know, uh, you can use it when your business process becomes more complex. So you can depend on it. However, the downside is that now there is more complexity in order placement, and it has to devise this logic that for it needs to communicate with the payment service, and it needs to communicate with the inventory service in order to fulfill this order placement task. So highly decoupled philosophy, which we usually follow in microservices architecture, is preserved in this way through this, front controller pattern. Still, order placement is all about order placement. Payment microservice is all about payments. Inventory service is all about inventory. It is just that as a workflow owner, when we need additional information from payment and inventory, then only that information is fetched, processed here, and then placing a purchase a book process is completed. The problem, everything looks good so far, but imagine when we were doing this, an error happens over here. So pay for order is already happened, and update inventory it could not succeed. What we will do? So error handling can be difficult in more complex business processes, but we do have, some mechanisms to deal with it. The basic mechanism is that you just depend on rolling. Either you let everything happen or you do not let anything happen. So that could be a way forward. But then in this order placement, you also need to look for such, uh, errors, and you have to handle those so that properly a complete transaction can happen. And if some error happens, then we have to redo the whole transaction. There are multiple, ways to deal with that, but we will not go through into detail uh, in this lecture, but it can be further studied. Now let us talk about another example of orchestration process. So it is also a complex process that we are dealing with, like place an order to purchase a book. And then in orchestration, as we discussed before, you got one workflow owner, and this one is actually a mediator in between. So this place order communicates with multiple microservices like order placement, inventory, and payment. And through this workflow that you know program here, uh, this communication happens. So a mediator is used to handle the complexity and coordination required for the business workflow. So everything, the coordination happens in this mediator that you have. The problem, as we can see easily, it creates coupling. Now we can see that all these depend on each other. Of course, this payment doesn't depend on order placement, but this place order depends on this, and this. So it creates decoupling between different services, which is, not which is not something we want to have in microservices. But we are not living in an ideal world, and such uh, workaround has to be there so that a system can work. So often domain workflows are inherently coupled, as we can see here. And what we can do is we can simply try to put these services close to each other so that uh, though these are, separate microservices, we can still consider them one big uh, uh, service, fulfilling the need of the business. Transactions, something, calling one or two or three microservices like that is all right. However, what you need to really avoid is a transaction across all the service boundaries. So you should not have a, microservices architecture designed in such a way that you depend on this service and this one and this one and this one. Almost all the services are involved. No, then it is not microservices. Then if you do it like this, then you are violating the service boundaries of microservices architecture. And the advice is that you should not do such design. You should not develop your microservices in such a way that in order to achieve a process, you are depending on all the services. So if it is the case, then it's not microservices. You are violating the basic principles of microservices architecture style. So don't do transactions in microservices. But how you can do that? You have to fix the granularity of your services again. So if you fix them right, then you will only depend on a few services in a worst case scenario, and then it will be all right. Exceptions always exist, and patterns exist that can handle, this kind of cross transactions also. And in such situation, if you really want to do something like that, then you can depend on something called saga pattern. Okay, so let's look at how Saga pattern looks like. So Saga pattern, it is for microservices architectural style, as you can see. By the way, also in this example, you can see that we are not depending on too many services. We are only depending on a few. So it's more like what I have showed you here. So this is also a kind of example for Saga pattern. So this one I didn't say, but this is also an example of Saga pattern. What you do in here, you got one main service here, and through that service, you can communicate with two or more than two microservices. Ideally, these services shouldn't be too many. So like for instance, in this service, you fetch data related to customer profile, you fetch data related to credit card wallet, and then when you are registering a new customer, you communicate with both services. So this example is precisely what we saw over here. So like place an order to purchase a book. So this is also an example of Saga pattern. So here an important thing is that, as I already discussed on this slide, that when error happens, it gets really difficult to control. So there are some mechanisms, but we will not go into detail. But one pattern or one framework to look up is compensating transaction framework. So what it does is that it tries to let all the transaction happen or nothing happens. So this is what we do in here. Okay, now finally, let us discuss the ratings of this architectural characteristic. By the way, partitioning type is domain based. It's a domain driven design. Actually, the most extreme one, really extreme one in domain driven design. Number of quantas, you can have one to many. One quanta for one specific domain concern. Uh, when if we look at all these things like deployability, elasticity, evolutionary, fault tolerance, modularity, reliability, scalability, testability, it is really high in those numbers. So it is a really, it is a very good architectural style for today's um, issues we have. So high backing for automated deployment, testing, and other modern practices. It relies on DevOps revolution that we have, the use of cloud to automate, our operational concerns. Uh, it is scalable, it is elastic, it is evolutionary. Like how it is evolutionary, for instance, let's say you just want to update some functionality related to customers, you just go to that microservice, upgrade that one, and the remaining architecture will remain intact. So it's really evolutionary. You can patch your system separately, it can evolve over time. So it's an evolutionary architectural by nature. Slowly and steadily, you can improve all these business processes within those microservices separately. It is agile, as you know, because again, you are targeting one small functionality at a time. So agility is also really supported. So where it is not shining, well, it is not a simple architecture. Simplicity is one star. It's a very complex architectural style, depending on too many components to work, to get it work in working. Overall cost is high. You need experts, you need expensive hardware, you need cloud services, and the performance is also low because all these communications usually happen over asynchronous in an asynchronous way, and asynchronous communication makes the performance, it makes it slow. So that is something to remember. So that was our topic, microservices architectural style. Now we are going to discuss the final topic of today's lecture, and that would also be the final topic of this course. So it is discussed in your course book in chapter number 18. How do you pick an appropriate architecture for your problem. And by the way, we are trying to do the same. We are trying to simulate that through our project. So choosing the appropriate architectural style. It is discussed in chapter 18. So one thing we have learned when we are discuss all these architectural styles, that there is no silver bullet. No single architectural style fits all scenarios. So what you need to do is you need to look at your problem. You need to look at the concerns your all the stakeholders have. You need to look at the domain needs. You need to look at the strategic goals, and then you also need to analyze the trade-offs. Then you can pick the right architectural style for your problem. So architectural styles actually have evolved over time. So we learned about some architectural styles that are really old, and we learned about architectural style like microservices, which is pretty new. It is not really new, like it has been around for like more or less 10 years now, but still it is relatively new. We can say that. So architectural styles evolve based on our past experiences, ecosystem changes, the kind of technologies and capabilities we have in our hand. So those actually, demonstrate, those actually make it trendy what kind of architectural style we should use. And we need to remember that just like fashion comes and go, these architectural styles also come to fashion and they come and go. But we need to look at our problem statement, we need to look at the needs, and then we need to pick architectural style that is best suited for our needs. So why architectural styles change over time? Well, it is because of past observations, our past success and failures over time. Like service-oriented architectural style was based on reusability philosophy. However, it turns out to be not very successful. Versus now, if we go to another extreme, we have microservices now that advocates share nothing philosophy, and all other architectures are kind of in the middle, in between of these two extremes. So in the past, the components, the softwares, a lot of mergers were happen, and it was important to reuse what we have. But in nowadays, recent times, the compute is becoming cheaper. Containerization technology that we have in our hand allows us to create, containers. And once we can create containers, we can think of microservices. Each functionality, business process, domain running in its own physical space. So here comes microservices in picture because of the technological advancements and the technology we have at hand today. Then ecosystem changes. So ecosystem changes also talks about very much similar, like I discussed about containerization. Kubernetes is actually an open source system that allows this containerization. So it is something we all need to study now, what Kubernetes is. And it's a technology, it's an open source technology. It allows us to do, perform containerization, and through programs, through proxies, gateways, we can start these machines, shut down these machines. So these operational powers that we have, we can have those through these, new ecosystem changes that we have, this new technology that we start to have today. And then, when we talk about Kubernetes, very much similar, with the part of that is Docker and serverless computing. So serverless computing, we have one lab on serverless computing on AWS cloud. So serverless computing, also sometimes called Lambda, is a compute you can have on some cloud, and through API, you can define some endpoints. You can perform those operations on that cloud device. So these new capabilities allows us to have uh, a system like microservices. And acceleration, now, rapid evolution of tools and engineering practices that we have these days, DevOps and all that. This also agile, a lot of, companies have moved to agile based development of software. That also, these actually dictate what kind of architectural style we should pick these days. Domain and technology changes, like, business industries constantly evolving, putting us new demands, asking for new architectural styles, and so on. And finally, cost, licensing, market trends. This also affects our decisions. Now, in 2020, like in 2015 or 14, if we look at that time, Linux servers starts to become widely spread. And Linux, the good thing about Linux is that these are open source operating systems, and these are very good servers. So that then open source kicks in. We have a lot of databases that are open source. So all the technology stacks we can depend on are available now free of cost. We can depend on those technology stacks, and that also dictate to different architectural styles like microservices that we have today. So these are all the reasons that actually changes the different architectural styles over time. So we end up developing new and new styles based on the needs of that time, and based on what we have available at that time period. How do you decide which architectural style you should pick? So let's say, well, you have to pick an architectural style, and for that you need to have domain knowledge. So what kind of industry specific needs your software will have? You need to think about that. What kind of architectural characteristics need to be met? Performance, scalability, readability, UI, and that kind of things, accessibility. You have to think about that before picking an architectural style. Data architecture, how much you are, depending on data. Is it data intensive application? How you will store your data, how data will be accessed, what kind of data it is. So what kind of, databases allows you to store that kind of data? So you have to think about that. For that purpose, you have to talk to your DBAs. You have to talk about, as an architect, you need to talk to your database administrators to find out more the needs of your application. Organizational factors, like how much budget do you have? What kind of expertise your team have? Imagine you have a team very good developing monolithic software, but they have no knowledge about cloud. So how can you use how can you develop something related to microservices if your team doesn't have those expertise? So you need to think about your expertise also, in-house expertise, what you can really do. And then cloud vendor restrictions, what cloud vendors provide you and how they restrict you. You need to think about those. Then operational concerns or processes, like what kind of agile methodology your company is using. Is your company still working on old ways of working like waterfall model, or are they accepting agile? Are they accepting DevOps kind of readiness? Is your team familiar with these DevOps operations, cloud technologies that we have? These kind of things also should dictate what architectural style you should pick. And then certain domains are good for certain architectures. So you have to look for that isomorphism, the similarities. What architectural style is good for the business needs you are looking at? Okay, so that should be like, if it is merger and acquisition, a lot of merge will happen afterwards. Still today, service-oriented architectural style should be the answer. So you have to look at, architecture, how what, the domain needs, which architecture is compatible with the domain needs. and then pick that one. You also need to decide, are you going for a monolith or a distributed architectural style? You have to decide that. And once you decide that, where you're gonna put your data, centralized in case of monolith or partitioned in case of distributed. Let's say in case of, microservices, as you saw that the database is also partitioned within each microservice. So you have to think about this. Communication style. Should you rely on synchronous communication, which would be much easier to implement, versus asynchronous communication that scales better, but performance can degrade? So you have to think about that also. So what we can do is in the beginning, start with synchronous by default and asynchronous whenever it is necessary. So now we are going to look at 3 case studies discussed in your coursebook. Okay. And we will see different, architectural diagrams. So the scenario we have, it is about the silicon sandwiches case study we started in the very beginning of this lecture, course. So silicon sandwiches. And the scenario is that a simple system with a limited budget. So we are constrained by budget. So we want to have a simple system. And based on that restriction, we are going for a monolith. Okay. So if it is a monolith, it could be a domain partition design or it could be a layered architecture. We discussed that also previously in one of the lectures. So let's focus on a domain partition design. So what domain partition design mean is that you got one component for purchase, one component for promotion, one component for location, one component for recipes, one component for inventory, managing inventory, one component for making orders, delivery is one component, and then you got all these UI components that discuss or that connects different components together, and you got one big database at the end here. And here you got, since if you remember, silicon sandwiches allows you to have customization. For customization, you can add, let's say, recipes related to Scandinavia, recipes related to Indian subcontinent, continent, recipes related to Middle East, and so on and so forth. Same thing. So these are the overrides. So these are the kind of hooks you will generate, and later on more domain specific or region specific components can be plugged in here. So in that we have this a modular monolith that builds on domain centric components. You got a single database, you got web-based components, UI components, and the design consideration that you need to look for is ensuring future flexibility. And how you do that? So your domain right now, your design consideration is that later on you can, since you are following domain partition design, you can migrate it into a distributed system. And when you take it to distributed system, you can convert easily this one to a microservices architectural style. So what you will need to do then is you can create one microservice for promotion, one for purchase, one for deliver, and so on. You already have done these, separated these components, and then you can separate your database also into multiple small databases. So that could be a future thing to look for. So this is the design consideration that actually help you to start with a monolith, but a domain partitioned monolith. So, and as I said, these overrides are just hooks that you generate or endpoints that you generate for individual customizations that can be plugged in afterwards through the with respect to the region it will be deployed in. So let's discuss also same silicon sandwiches, but microservices architectural style. Remember that microservices is also a monolithic architectural style. Microkernel architectural style for customizability. Why? Because microkernel allows you to have custom components within. So you got a one core functionality and all other functionalities can be added as plugins. So remember that. So customizability is one of the key requirements. So scenario we are looking at. So here the scenario we were looking at was simplicity and limited budget. So that forces us to go for a monolith domain partition design. Why we go for domain partition design? So that when we have a lot of budget later on, we can move to microservices architecture easily. Now our scenario is customizability is our key requirement. If that is the case, you may want to implement microkernel. In that case, what you can do is you can have the core functionality in the middle, and then you add additional functionalities, customizable components as plugins. So this can look like this. So you can have one core system, let's say providing purchase and delivery, and then you can have some common functionalities here related to recipes, inventory, promotion, location, and all the local plugins like one for South Asia, one for Scandinavia, one for maybe Middle East, one for Japan. They can be added here separately uh, as plugins. So in the microkernel architectural style, you have this one database, main database connected to your core application, and then all these local plugins that you add in later on can have their own small local databases. So now through that, what we can do is consider, it's a microkernel architectural style. All these functionalities are exposed through the API layer. Maybe it's a RESTful API, and one component is for the iOS, one component for Android, one component for JSON. So it just produces, the JSON. Anyone can consume it, and one component for the web-based application, or maybe three components, as you can see. So if I expand this local part here, that local part can become something like this. So here you got common functionalities. Then you got this local one, local two, local three, all that, these can be plugins. So this is your main core system, the bare bone, and then you can have this common as a plugin and some local functionalities or depending on the region separately as plugins. So as you can see that through this plugin, you provide the bare bone recipes, common recipes, inventory, promotion, locations, and then through these, one for South Asia, one for Middle East, one for Scandinavia, you can provide specific recipes, inventories, promotions, locations to that countries and regions. Now let's move on and look at gone application. It was about, the bidding auction system. And the scenario, let's look at scenario. The scenario we have in our hand is the application should be high scalability, should support high scalability and performance. Two things, scalability and performance. And whenever you have these two things, elasticity, scalability, performance, you end up with these two options, event driven architectural style or microservices architectural style. So in here, let's try to put it as microservices architectural style. So so here we can have one component for, uh, yeah, so over here we can have, this main bit streamer right here. And here we can have a video capture, communicating sometimes to video streamer here. And then we have this bit capture. Actually, it is not fully microservices architecture because as you can see, database is only, in three places. Not every service has access to database. The idea is that this auction microservice depends on this database through this queue that you have. So bit tracker has the data coming from auction session and auction capture. So anything about auction through capture and session is stored here on this database. Also bit capture through this channel goes and stored here. And then when the data needs to be updated through that bit streamer, it can go here and go here. And through bit tracker, whatever needs to be synchronized here, it goes from here and it is updated here. So here we can see that in API layer, since microservices architectural style um, advocates heterogeneous components, so this communication happening here is, RESTful. Here it is AMQP. Here it is a BLS, and here it is RTP, remote, transmission protocol, and so on and so forth. So here you can pick, microservices. For instance, if you pick microservice architectural style, then you can have that for handling different kind of workloads. Communication choice can be mixed, synchronous and asynchronous, and then message queues can be used for adding reliability to your system. And then you can also define quanta boundaries. Like quantum, one quantum means one physical manifestation of something. So look here, as we saw that this one was relying on this database here. We can put this auction session and bit tracker together. This color tells us that this is just one quantum physically close to each other wherever we deploy them. Similarly, you can see like, based on that, you can combine some of these components together like these two. These two are physically close to each other. And then these two, I think, yeah, this one is just one, this is one, this is one, and this is one separately deployed. By the way, it is only one of the correct designs and you can have as many as you want. All you need to do is you have to have the least worst set of trade-offs when you are designing your architecture. So key takeaways. So no architectural style is inherently best. It depends on the context. Choosing an architectural style actually depends on balancing the trade-offs. Monoliths are simpler, but distributed systems scale better. So simple systems you want, go for monoliths. You want scalability, go for distributed systems. Synchronous communication is easier, but asynchronous scales better. Okay, but asynchronous communications become slower. Flexibility is the key. So design for future adaptability. Even today, if you pick a monolith like this one, try to design your system maybe domain-based, using domain-based partitions, so that in future it could be converted into event-driven architectural style or microkernel architecture. Sorry, this these microservices. So understanding architectural trade-offs leads to better design decisions. So with that, we finished today's lesson. And with that, our lectures are also covered. Of course, we will keep communicating through our lectures and I mean our tutorials for different assignments and um, project tutorials. So any questions you have, please feel free to ask.
I have a question
Yes,
about
please.
the self-assessment questions
Yeah.
in the book.
Yes.
I think for the first half of the chapters, they are pretty
Mm-hmm.
uh, good,
Yeah.
but when it comes to the different architectural styles,
Mm-hmm.
there are there's a lot of questions for each style, and many of them are pretty specific. So I'm
Yes.
wondering
Mhm.
how should I think when I
Yes. Yes. Do you see my screen, by the way?
yes,
Okay, let's go there. Okay, what I mean, what I suggest is that go here and look for the past exams. I mean, over here, let's see the final exam. Yeah, let's go here. So I'm going to open one exam. Okay, let's open this one. Okay, let's see what do we have there. So there were some multiple choice questions, but I will not give multiple choice questions this time. I said it on the same page. It will be just short answers and some scenario based questions like this one. Yeah. So that is one short question. Lack of cohesion in method 2, ALCOM. So let's look at this one. Why is it more important for an architect to focus on technical breadth rather than technical depth? So it is in the first two chapters.
yes,
That one is pretty easy to answer.
yep,
Yeah, so implicit. So I will try to give questions which we are repeating a lot in the, like elasticity, scalability. I mean, we have learned so much about these two quality attributes. So I assume you should be able to answer these. But then after, these short questions, yeah, three challenges that distribute very pretty, common question. If you listen to the lectures, listen to the videos I gave you, you will be able to answer. And then comes some more questions where, like as you said, I try to give you the diagram so that you can have something to hold on to remember what we learned. So orchestration and choreography, we studied that today, right?
yep,
In microservices. And then I gave you an image so that you can recall what how microservice architecture look like.
yep,
And then I ask a question. What is the question? Okay. What is the difference between orchestration and choreography in context of microservices? So this is how I plan to help within the exam, like trying to give you something so that you can remember what is it about I want you to answer. And here you can, now feel free to, it's a 4 point question. Feel free to give an example. We have seen two examples for orchestration today, two examples for choreography today. So, you can um, name, you can use those. You can simply write descriptively. It's up to you. And yeah, then here is the case study. But before I give a case study, what I did, let me see. Yeah. So did I mention? Yeah, I probably mentioned consider the following description and architectural diagram for Eclipse SDK. Each subsystem in the platform is itself structured as a set of plugins. So plugins. So it's a microkernel architectural style we are talking about. So what did I ask you? Let us see. Okay, okay, then. Yeah, here are the questions. Using the diagram, explain microkernel architectural style. Pretty easy, I would say, right? Do you agree with me or
mm.
not?
I pass on the answer on that one.
Yeah.
I don't remember exactly the different styles yet. I haven't gotten that far in the book yet.
Yeah, but you see,
Mm,
I gave you, it's a microkernel. So
yes,
I really, I'm not, trying to pinpoint some corners within the course where you have to struggle. Okay, this question where I did, where did we study that? Maybe I'm trying to ask questions where we discussed again and again many times. big
Okay.
things. So
Yep.
focus on big things, and then you will be able to answer these questions. Like, look at this one. Explain how the following quality attributes positively or negatively impacted when this architectural style is used. Fault tolerance, overall cost. So that means we studied about how many architectural styles we studied. There are like, maybe 10 or 12 architectural styles. When you are preparing for those, uh, read that page so that you remember what characteristics they offer. So this is a page I would try to, revise through 2-3 times before coming to exam. And I would do the same for a service oriented architectural style. I would do the same. I will go here, topology. If I ask you a question, I will provide you the topology. And then I may ask you a question like, okay, what is this enterprise service? So you should know what enterprise service is then. And I could ask you, what is the context in which service-oriented architecture was developed? So we discussed that also a lot. And then reuse and coupling. I can ask you that. And finally, I can ask you something about this. Okay, you got service-oriented architectural style. Here is the diagram of that architectural style. Could you please tell me why it is performing bad or good, on some of these architectural characteristics? So that would be, the way I will ask you questions. Let's look at some questions here from, let's say, yeah, microservices. We just studied today. See, bounded context. So prepare these 10 questions and you cover everything. When I say prepare, if you read these slides and read the chapter, I think you will be able to answer my questions. Okay, does it
Yep.
help?
Yes, I think so.
Yeah, great. Yeah.
Will the exam still be 60 points, or
Good question. Let me
since
see.
you
Yes. Okay.
took away
Yeah.
the
Yeah.
multiple choice ones?
What I will do is I will announce here. I mean, it's not mentioned here now, only I said that there will be no multiple choice questions. So I will prepare an exam and then I will make an announcement explaining the breakdown, how many questions, and I will give you some more details
Okay.
when I'm preparing, when I'm done with the exam.
Yeah.
Okay. So please look at all these 3 exams. Let's look at this one. And yep, do you remember this one? We did that. This is also same LCOM2 question. That is about quality attribute. So you did that exercise in assignment 1 also. Quality attribute scenarios, how you measure them. If you just read them once or twice, you should be able to answer. Like, let me see what I'm asking. Yeah. So what is meant by terms response and response measure? Yeah. So response measure is this one and response. So you should be able to answer this. Then comes this part, some scenario like questions. And this one is more aligned with your project that you are doing. So here I define a simple system, e-commerce platform, and then I ask you about concerns like scalability, elasticity, performance. And then I ask you question like how good or bad space-based architecture is for this kind of problem. And then I ask one question about event-driven architectural style. But these questions are not really something you have to really remember. These are more like general questions about these architectural styles, like synchronous communication. What are the advantages of having that in event-driven architectural style? If you go through the lectures and read book, you will be able to answer this question. Yeah, what are the characteristics not well supported by event-driven architecture? Same thing. You need to check for this page that we have, like where we discuss those characteristics. So yeah, it will be a little bit of work, but not too much. I hope so. Okay, does it
All
help?
right.
Yeah.
Yes, I hope so.
Okay. Okay, nice. So um, with that, see you in other tutorials then, and take care.
Yep.
Bye bye.
Thank you very much. Bye
Uh,
bye.